All right, my name is Felix Schaller. I'm the developer of the Aeroflexible profiles, and it's going a bit different direction in aerodynamics, a bit away from laminar profiles, more into adaptive profiles. They are no longer rigid, and but adaptive, as you can see here a bit in a little schematic graphic. And it's a bit inspired by bionics, and because birds have very agile flight behavior, which is not yet reached by technical means, and so the birds are still better in aerodynamics than technical planes. So the idea is now to get more advanced in the realm of what is able by nature. So okay. If you have a normal plane without pitching it, it will go like this, having the nicking of the flight track. So the plane rises, it loses speed, then it happens to stall, it bends the nose, and then finally it takes time until it reaches lift again. And by that you're getting very awkward flight maneuvers, and your profile is very sensitive to these conditions, and creating stall and lots of other disadvantages. So here you can see a little test flight, a bit illustrated with different stages. And so now is the question how we can make this better. And today we have rigid profiles, and they cannot deform, so as I already mentioned, and this is a problem. According to the different flight stages, speed and attack angle, they demand a different aerodynamic deflection of the air based on their inertial movements around the object. So these features I already mentioned in the beginning, that there is no ability to adapt on the dynamic features of fluid dynamics of the current profiles. You need a normated profile which is designated for your certain operation field. If you are a cruising plane, a passenger plane cruising at 800 kilometers per hour, then you need another profile. And when you're a soaring pilot and wants to soar at 100 kilometers per hour, did I come in? And this is making the profiles of very, very sensitive to stall conditions, and also in unsuitable flight modes you get a lot of drag on the profile surface. And that's a bit the sorting of the 1 second. No, this is how you can explain it. In the past, we have in the last 100 years we worked more with the potential theory with Bernoulli and Kutashkovsky, and Prandtl developed a lift theory, which are more mathematically abstracting the flow around the profile, and but is in order to describe stall conditions and turbulent behavior, it's not so good model to describe these features. But with Newton you have better abilities to describe certain stages on a profile, to describe when it comes to a stall mode or stall situation. And this can very good answered also with classic technical mechanics extending into fluid mechanics. There are some people published some discussion about understanding flight with Newton mechanics, well, there's often a problem arguing lift with Newton, because you only often think deflecting air on the lower side of the wing, but also the upper side of the wing has 2/3 impact of the force creation for lift, and you can describe how this is achieved on the upper side by you have a convex surface like on the Coanda effect, and how the Coanda effect happens mechanically is that you have an inertial motion of mass. They normally, based on the Newton laws, wants to go straight, but inside air you have an energy potential you can motivate or you can activate to deflect your air back onto the surface, and this gives a certain acceleration you can activate out of the potential air energy of air, which deflects your air back onto the surface, and by that creating a little laminar bubble in between, as you can see here. If I overdrive the convex surface in an edge, but here you can see that the air cannot follow straight the surface, but has to be deflected in a certain distance, following in a steady path the surface again. If the altering of the surface change is small enough, the air has not enough. The potential energy has not enough energy to make short enough curves inside the laminar separation bubbles, as you can see with if the angle of the surface alteration increases. Finally, the air can manage to turn around inside the laminar separation bubble, creating a stall condition where you can outbalance the low pressure fields here, which causes then stall. And so you can see then again that the air is no longer following the surface and giving a steady impulse change downwards, the downwash of air behind a wing, which causes your lift as a contradictory force. So you don't have no longer this downwash, but just turbulence behind a wing, which now not causing you any downwash anymore, and that's what causing the stall condition. I want to add another feature. Maybe I forgot it. Okay. So also to avoid this, in past years, we created some kind of flaps. They stabilize a little bit the area in the front where the most pressure peaks happen when you are in low cruising speed or stall speed. Then this little air channel is also avoiding that the reverse flow can reach the nose, the leading edge of the profile. So these planes could cruise at about almost 45 kilometers per hour, but they were not so versatile in higher speed, because all the planes couldn't put these flaps in. New planes now are able to put these flaps inside the profile back into the profile. But it's a very rigid and static solution, and it's not answering the individual fluid dynamic situation. So here again you can see when you rise the technical almost normal flight mode, you have pressure gradients, but if you rise the pitch angle, the pressure is more concentrating in the front. It's very good to understand with the Newton idea of deflecting the air based on the energy potential inside the air, and because of the attack angle rises, then the pressure as a contradictory result is rising as well, because this is actually the low pressure. You can also answer that it is the rest of the force which is left when you want to deflect the air back onto the surface. So you withdraw this pressure from the energy potential you need to deflect the air back down to the surface. So this is, and here you can see again in a laminar situation you have a downwash. Oops, sorry. You have a downwash, and here there's no longer a downwash achieved, so you have just a turbulent situation behind your wing, and it's not giving you any more the lift as a contradictory force, because you're not deflecting air back down. And these inertial effects in air also affects the ideal fluid body. So if air wants to flow around an object, it has not the optimal flow path. You can see here, this would be the ideal shape for the same object acting in the fluid. But because the air has only an ability to deflect the air around steady paths, you see that the air has to develop certain contradictory forces in vortices who are filling out these areas where the body is not able to fill out, and so this is a very this is one of the facts why you get drag on a profile or any other aerodynamic body. Because you have not the suitable form to deflect the air on a smooth path according to the energy potentials there are inside the fluid or air. So how we can solve this, as I already introduced, creating surfaces that are able to reshape itself and fill out these areas where you have here, where the surface wants to get in between this turbulent field and fills out the areas where normally turbulence happens. And these Aeroflexible profiles, as I call them, they are acting passively because of these aerodynamic conditions of the inertial forces forming the ideal flow body around the surface, and it's also in a critical situation it can avoid reverse flow, because when the air wants to return on the surface, these elements lift up and avoid or delay the stall for a certain degree. So the first tests made with such kind of application was the Bionic Institute in Berlin. They introduced a flap in the backside of the wing with some flexible self-actuated features, but they had the disadvantages that one flap created unsuitable deformation of the profile, which they only could fix with porous material. So then there were further research made by another PhD student, and in 2003 also a PhD student made CFD researches on the research is based on the Bionic Institute made in 1996, and I advanced now the abilities to form a total profile with these kinds of flaps, and also by that creating an individual aerodynamic body by these features. So this is how it looks like on a test plane. where I applied flexible elements on the surface. They are able to deform mechanically independent, because if you have a kind of not with shells of the surface which is connected, then if it deforms, it creates wrinkles, and this is making your profile surface. It makes it. The wrinkles destroy your profile shape. But if you have individual flexible elements, they are reacting individually, and by that creating a surface expandation without any forces in between. So okay, now there's a different flight behavior of the wing without with the flexible elements, and you can see that you have a much smoother path, and also the distance is fairly longer in the distance, and so this is again a picture of the status of the Aeroflexible profile. In normal mode, you have more flat laying elements on the base of the wing, which carries these elements. It doesn't have to be a profile at all. It's just a carrying element, because the profile shaping is done by the flexible elements on top of the wing. Finally, if you go into star mode, these elements lift up and try to avoid the reverse flow from going into the leading edge. So this is another high-speed camera analysis. If you on-board camera, where you can see the different behavior of the flaps deforming and shaping profile. It's still not perfect because these front flaps, they are still very rigid. So and these are too long. They have to be cut a bit. They have to be cut a bit. But so there are some results made and been applied on a second profile, which is yet applied on a wind tunnel. And here's some wind tunnel tests with the new profile, showing the different behavior. This is a rigid profile. As you can see, it starts very, very fast, fluttering in the turbulent stream, and you cannot really control it. It's very aggressive acting, and gets stall and drops and stalls again, and so you get some kind of amplification of this behavior. And that also explains a bit why you have on soaring planes this noise because of the wing torsion at the end. So that's causing the singing noise when they flying into the air, because they create a vibration. And this again, on as contradictory example, the flexible profile, it shows a very stable behavior inside the stream, and also in this more stall mode, you see what's happening on the surface, that the profile tries to avoid the reverse flow, and also on the lower side the elements come up and sometimes try to increase the lift by a certain degree. And these are examples in the nature showing the same effect, where you can also see from below that the feathers come up and increase, and here is now going in the lower feathers, and they increase the surface of the wing in these very steep angles of it's a very steep flying maneuver, and which a plane wouldn't be able to manage at the moment. Not yet. This means that this profile also is no longer a laminar profile. As you can see in soaring plates, you go more into slim profiles because you want a longer laminar path on the surface, and then you go in the width of the wide wingspan to create enough lift for your plane. And by that, having a shorter profile length, you want to achieve at the certain Reynolds numbers a longer laminar distance on your wing surface. But there are certain arguments why laminar surfaces are not the best. The one argument you have in every soaring competition that you have little insects hitting your profile and then destroying your laminar boundary layer. There are some technical advantages with you can clean it in the air, but no animal has this actually. So there are no animal having laminar profiles. Sharks, for instance, where it is discovered first, and also tested in wind tunnels, that they have significant higher or lower boundary layer friction according to any smooth surface. Also, dolphins, you would think, well, they have a smooth skin, but it's only half true. The texture or the behavior of the skin is very soft and can be formed by a certain fluid dynamic interaction with the water. And also penguins have developed another technique which is also very similar. They put, when they are escaping predators, they put little air bubbles inside their boundary layer, because they store under the feathers, they store a bit air, and when they want to escape, this air gets released and creates a little very fine bubbled boundary layer, which has a very good friction values, much better than any laminar surface. Also, we say that the penguin has the best shape for its conditions where he operates in the water. But also these bubble features, they make a great impact, and also the feathers as well, creating micro-turbulence boundary layer. And you can say that micro-turbulence boundary layer act a bit like a ball bearing effect, or a ball bearing incorporated to not a bearing without balls. And normally you say laminar friction is the best instead of turbulent friction, which has a lower flow speed for instance, in a tube. But as you can see here, or when you make a diagram, you can see that in the lower areas, or very near to the surface, the turbulent boundary layer is faster than the laminar boundary layer, which is not that fast on the near surface. There's a certain answer, or there's a possibility to answer this contradictory paradox. Is that actually these two behaviors are physically total different. Where you have more laminar, it's more physical feature, like maybe deforming or molding a certain mass, where a turbulent feature is more like having a mechanical feature where these turbulences roll upon each other. The only disadvantage on turbulent motion, turbulent boundary layer, is this, that they create higher amplification, and by that absorbing impulse out of the stream and store them locally. So this is, you can say actually that a vortex is a complex resistor, which is having then a higher inertia, because by the same cruising speed of a laminar stream or a turbulent stream, the turbulent stream has an internally higher motion than if you make you take the mean speed of the flow. which has a lower impulse energy if you count every particle inside the turbulence. And so this is a bit showing amplification of turbulences. They create clusters at the end, turbulences inside turbulence, and by that trapping more and more energy out of the stream, and this is mainly causing the friction in a turbulent boundary layer, and not the actual viscous friction. So here you can see a bit kind of diagrams I got by the University of Stuttgart. It's by Ulrich Rist. He donated me this picture, and so you can see here at the beginning, here is not so good visible. Normally you have here Tolmin Schichting. They try to evolve higher waves, and finally you can see that they evolve a breaking point where it's like in a beach, the waves break finally, and then because the laminar boundary layer before cannot revolve in the turbulent motion, they try to increase by making bigger and bigger Tolmin Schichting until they can revolve. So you can also see in physics, every body wants to go the lowest way of resistance, and so you can also say why a laminar boundary layer collapses very fast if they have the first ability to collapse in turbulent motion, because it's for them actually mechanical more or less it's accompanied with less friction in terms of laminar shearing, which has actually inside the fluid a higher friction. So that's why they collapse. But then this in a disadvantage, they amplify and by that withdraw impulse energy out of the stream. Okay. So this is, also in golf balls you have these features. That's also they lay longer on the surface, and by that also create less friction in the near boundary layer. If you have you create a ball bearing effect, then you can avoid that the vortices amplify. Like here, you have a little piece on the surface, like a insect impact, and they at that point create a reason for the laminar surface to revolve inside turbulences, and by that amplify each other. But if you have a kind of small structure which causes organized little turbulences, then you get maybe this kind of stream motion where in the nearby area the vortices mix in between each other. They get breaking. They break behind edge, get sucked inside the vortex center, and by that go outside and revolve in a bigger vortex and go back and again repeat from the beginning. And so you can create a kind of rolling effect in the middle where it's like a ball bearing effect, and by that creating better laminar surface condition. So the conclusion would be that you don't need. You can make other designs of wings, like on this bird. You have flexible features, and also could go more in length because the laminar conditions are no longer so important for your aerodynamic conditions, and also going more into flexible features. You have much more abilities to coping with that dynamic feature, or they are inside the air. Okay, that's the end of the presentation. If you have any questions.
Yeah, there's a lot of examples that show that turbulence or micro-turbulence has reduced the friction or the air resistance.
Yeah.
With your own construction, could you confirm that with own measuring results?
There are many researches done in this area where it's by testing in the wind tunnel is our results. I can show up to you the tests of the tests that they made with shark skin effect, or the Fraunhofer Institute developed surface which riblets inside on the top with very low diameters, and they also could achieve 10% less boundary layer friction. And there are lots of also publication. This was done with dolphin research by the Bionic Institute in Berlin. They did some research, and also the University in Stuttgart did some dolphin skin research. And
if you're being with the microscopic flaps, could you have your measuring results too?
You mean the flexible? The flexible. There are some measurements yet made, but they are not dependent on tag angle and so these fine measurements they have to made still. In the wind tunnel, which is I finished a few weeks ago, so there's these results have to still be made. And if you follow my Facebook channel, I will publish everything there. What is coming up in the next months, and also the next step would be making these CA and CV diagrams compared with the normal profile. But due to time, they were not yet finished, but they will soon be finished on the channel. So okay. Good.